Hello friends, in today's session we are going to solve two questions. One is from year 2001 and second one is year from the 1991. So in the first question, an inductor of inductance L which is given as 400 millihenry and resistor of resistance is R1 2 ohm and R2 2 ohm are connected to the battery of EMF 12 volt as shown in the figure. The internal resistances of the battery is negligible. The switch S is closed at time t is equal to 0. What is the potential drop across L as a function of time? After steady state is reached, the switch is opened. What is the direction of and the magnitude of current through R1 as a function of time? So we are given of this figure in which we have R1 is given as 2 ohm, R2 is also given as 2 ohm and inductor is given as 400 millihenry and we have a EMF of 12 volt and a switch S. So this question is basically into two parts. First one is says that at time t equals 0 the switch S is closed, and that moment we have to find out the potential drop across R as a function of time. And the second case, when the steady state is reached, then the switch is opened. So we have to find out the magnitude and the direction of the current through R1. So in this case, we have to remember one important property of inductor, which says that the inductor doesn't, you can say the initial condition of inductor is equal to the final condition of the inductor. Or we can say the inductor doesn't change its condition instantaneously. So let us start for the first part. At t is equal to 0 positive, the inductor will behaves as open circuit, and this we can just write the reason for that also. We can say the current through the inductor, if that is IL, cannot change instantaneously, Therefore, the inductor will be acting as open circuit. So from here we can say that the entire voltage which in this case is represented as E appears across L, the inductor which is L. Therefore, we can write the voltage across inductor at 0 positive will be equal to 12 volts. Now, we can discuss the same thing for t greater than 0. For t greater than 0. Now, for t greater than 0, the inductor will be now in series with the resistance R2. Under this condition, inductor and R2 are in series. So this is our series RL circuit, series LR circuit, and we know that the time constant for this circuit if represented as tau, then this tau can be written as L upon R2, which will be coming as 0.4 divided by 2, and this will be equal to 0.2 seconds. Therefore, we can write the equation that the current grows through this LR circuit, and the equation is simple because now the circuit is consisting of inductor and a resistance. Inductor is given as L, resistance is given as R2, and if we say the current flowing through it is given as I R2 and is a time dependent IR2t. So therefore we can write the equation as IR2t will be equal to I naught, that is our E upon R2, 1 minus E, and this comes as minus T upon tau. And E, we substitute the values. It is given as 12. We have 2 ohm resistance, 1 minus E, and tau we just calculated is our 0.2. So we can write our current through the series combination of L and R2 will be equal to 6 1 minus e raised to power minus 5 t. Now we can find out the voltage drop across inductor. If that is written as VL, then we can write voltage drop across inductor is our VL, then VL will be equal to L current through the inductor, that is IR2t divided by dt. Inductor we will know is given as 400 millihenry, so that will be 0.4, and this comes out d of dt. Substituting equation for the current, this is a 6 1 minus e raised to power minus 5 t. So we get our VL will be equal to 0.4 multiplied by 6 multiplied by 5, and this comes as e raised to power minus 5 t. So this is equal to 12 e raised to power minus 5 t, and we can write this as VL as a function of time will be equal to 12 e raised to power minus 5 t. So this is the equation of the inductor as a function of time when the switch is just closed at t is equal to positive. Now we come to the second part. In the second part, we have to find out the current through R1 when switch is opened in steady state. Now it is at steady state condition. So steady state condition means, so in this case we can write the circuit was in steady state before switch is opened. Before switch is opened, and under steady state condition the inductor behaves like a short circuit. We can say at steady state inductor behaves like a short circuit. So under this condition, under steady state condition, we can find out the current through R2, current through R2, if we can write is IR2 will be equal to EMF divided by R2. This comes as 12.2, coming as 6 amperes. And similarly, we can find out the current through R1. Current through R1, IR1 is equal to E upon R1. Once again, this will be also coming as 6 amperes. Therefore, total current from the battery will be equal to IR1 plus IR2. Total current from battery, if we write it as I total, this will be equal to IR1 plus IR2, which is 6 plus 6, giving us 12 amperes. Now the switch is opened. Switch is opened. So in this case, the inductor and the, you can say, R1 along with R2 forms a new LR circuit. Under this condition, as soon as the switch is opened, you can write the inductor, which is our L, and R1 plus R2 form a new LR circuit, or LR series circuit rather. Series circuit. And once again, the inductor will resist the change. So the current that was flowing through the inductor was 6 ampere. Therefore, the conductor, once again, the initial current through the inductor will be equal to 6 ampere. Therefore, the initial current through inductor, let us call that as IL0 negative, will be equal to 6 amperes. Now we can just draw an approximate diagram for that also. We have this R1 and this is our inductor, and we have our R2. Now this comes as a LR circuit. This is our LR series circuit, and R is equal to R1 plus R2. So therefore, the inductor in this case will decay through the series combination of R1 and R2. You can say the inductor current decays through series R1 and R2, that is R1 plus R2. So we can write the time constant let us call it tau prime, will be equal to L divided by R1 plus R2, L is our 0.4, this is 2.2 plus 2, giving us 0.1 seconds. Therefore, the current through R1, which will be now the decaying current, we can write the equation as IR1 T is equal to IL 0 e raised to power minus T upon T tau prime. And we simply now substitute the value, get R1 T, we have this as 6 e raised to power, and this comes as T, tau is our 0.1, so we can write as 10 times T. And we also need to find out the direction. So the direction of the current, through R1. So before switch was opened, the current was flowing in the downward direction through R1. Before switch was opened, current flowed downward through R1. And when switch is opened, the current will be flowing now in opposite direction. When switch is opened, the inductor tries to maintain the same current. The inductor tries to maintain the current. Therefore, the current through R1 reverses direction, or we can say upward. So we found out that this current will be flowing upward. So herein there was the important property of the inductor that it tries to resist the sudden change. So initial condition results in the final condition for a fraction of second. Now we come to the second question, which was asked in the year 1999. And in this case, the question is, the magnetic field B, which is given as B0 y divided by A k unit vector, is acting into the paper in positive z direction. B0 and A are the positive constants. A square loop EFGH of side A, mass m, and resistors R in xy plane starts falling under the influence of gravity. Note the direction of xy in the figure. We have to find out three things. First of all, the induced current in the loop indicates its direction. Total Lorentz force acting in the loop indicates its direction. And finally, we have the expression of the speed of the loop Vt and its terminal velocity. In this case, we are going to assume that at any time t, the center of the loop is at a particular coordinate, and based on this we are going to adjust the coordinate of E, coordinate of F, coordinate of G, as well as coordinate of H. We say that at time t, the center of loop at xc and yc. So therefore, we can write that the vertices, first vertex is our E. So we can write E as will be equal to xc minus a by 2 yc minus a by 2, and for vertex our F, we can write is xc plus a by 2 yc minus a by 2, and for G we can write as xc plus a by 2 and yc plus a by 2, and finally we can write our H vertex will be xc minus a by 2 and yc plus a by 2, and it is given the velocity is in downward direction. It is falling freely under the action of gravity in the downward direction. So we can write that the velocity v is equal to minus of v j prime, and which is in downward direction. Downward. Sorry, 1 second. Yeah. So in the downward direction. So let us start with part A. Induced current and direction. Induced current and direction. Yeah. So we have this induced current and direction. So first of all, for that we need to find out the flux, and then we can find out the everything. So let us start with the magnetic flux, which is our phi, and it will be given as integral of B and small area dA, and we can consider that dA is our area vector. So we can say the area vector, which is given as dA, will be, or we can write it as dA and k prime along with the direction, because our magnetic field B is along k prime. And we are also given that the magnetic field is given as our in z direction, which is equal to b naught y upon a, and this direction is also k. So from here we can clearly understand that our magnetic field is dependent upon y. Okay, so from we can say it varies it varies with y. So therefore, we can find out the bounds of the loop. So we can say loop bounds, and the loop bounds are from y to yc minus a by 2, and so for our loop bounds, so we have y from yc minus a by 2 to yc plus a by 2. This is our y coordinate, and we can find out that our x is from xc minus a by 2 to xc plus a by 2. So this is the loop bound for x as well as y. Therefore, the flux phi, it can be written as a double integral of our b naught y divided by a, and this comes as dy by dx. And we put the limits yc minus a by 2, and this is our yc plus a by 2, and here we have xc minus a by 2 and xc plus a by 2. So let us first of all solve this inner integral. So we are going to consider this inner integral and try to solve this. So we say inner integral which is our yc minus a by 2, yc plus a by 2, and here we have b naught y divided by a and derivative of y, and this can be written as b naught a, and this comes as y square by 2. This is yc minus a by 2, and we have here yc plus a by 2. Now we substitute it. We get this as b naught a, and 2 we can take as common, so we can write this as yc plus a by 2 whole square minus yc minus a by 2 and its whole square. Therefore, we get this inner integral will be coming as b naught upon a. And next we are going to my mistake. Let me solve it. So we can say this will be coming as our b naught upon 2a, and we are going to get this as yc square plus a square by 4 plus ayc, and here we have minus, and this is yc square plus a square by 4 minus ayc. This will be equal to b naught upon 2a, and here our this yc square and yc square is going to cancel out, as well as a square by 4 and a square by 4 also cancel, and this comes as 2ayc. 2ayc, and this 2a cancel with 2a, and this comes as b naught time yc, and this is our only inner integral. Now we are going to solve for the outer integral. outer integral we get our phi. The limits are xc minus a by 2, xc plus a by 2. This comes as b naught yc, and here we have now dx. Now this is quite simple. We can also just write it directly, and this will be coming as b naught yc will be common. Inside will be going to get our dx. We substitute the limit xc plus a by 2 and xc minus a by 2, and this xc and xc are going to cancel out. So we are going to get a by 2 plus a by 2, which is nothing but a. So we get b naught yc multiplied by a. Now we can find out the EMF. So our EMF, E is equal to minus d phi upon dt. Now it is given that the entire loop is falling in the downward direction with the velocity v. Therefore, we can write in the equation that our yc will be equal to y naught minus v times t. And because we know it is falling and we are given the velocity, and which is nothing but magnitude of this one. So from here we can write that our dy upon dt will be equal to dyc upon dt will be equal to minus of v. Therefore, the induced EMF, so we can write our induced EMF is equal to minus d phi upon dt is equal to, we get this as, we substitute value of phi, which is b naught yca. So this comes b d upon dt, b naught yc upon a, which we can write as b naught a, and this will be about dyc upon dt, and dyc upon dt is our minus of v. So we substitute it, we get the induced EMF will be equal to minus b naught a and minus of v. This gives us the induced EMF is equal to b naught a times v. Now we can find out the current. Current is equal to I will be equal to induced EMF divided by R, and we get this as b naught a upon v divided by R. Okay. So this is the current, and in order to find out a direction, we clearly see that this EMF is our positive. So we can say EMF E is greater than 0. So basically the flux decreases as yc decreases. Therefore, the current opposes the decrease. Opposes the decrease, and the current because of this will be in clockwise, or we can say from E to F to G to H. Okay, and it is viewed from the top along the positive Z direction. When viewed from above, that is our positive Z. Now we are going to find out the part B, and part B is our Lorentz force and direction. Lorentz force and its direction. Now current we already know, we just found out that the value of the current I is equal to B naught A times V divided by R, direction clockwise. So it means the force on each side, because we have four sides, so we can say force on each side. So first of all, so let us find out the force EF, and that is our to the bottom side, and Y is equal to our YC minus A by 2, and we have our X is from XC, sorry, X is from minus A by 2 to A by 2, and we can now directly find out the magnetic field, because the magnetic field B is given as B naught Y upon A and K unit vector. We substitute value of Y here, we get B naught, and this comes as YC minus A by 2 divided by A, and here we have K unit vector. So the force F on the side EF, we are going to calculate this is IL multiplied by B, and our L will be along the length is our A and along I unit vector. So we substitute the values, we get this as I, and this is our AI unit vector cross B. We substitute the values, and this comes as our I A into I unit vector, and value of B is our B naught YC minus A by 2 K unit vector divided by, let me check if it is A or 2A. Yeah, it's only A. So we have this as divided by A, and this gives us I B naught, and we can say this will be YC minus A by 2, and we have here I cross K, and which will be giving us minus of J. Now we can find out for the side GH, which is our top side. So our Y is equal to YC plus A by 2, and we have X is from A by 2 to minus A by 2, and here the side will be now in minus A of I. So once again we can write our magnetic field will be equal to B naught, substituting value of Y, YC plus A by 2 divided by A, and here K unit vector. Therefore the force on the side GH will be equal to I minus of AI cross B naught YC plus A by 2 K unit vector divided by A, and we can write this as F GH will be equal to I B naught, and here we have YC plus A by 2 and J unit vector. And now we come to our FG side, which is towards the right, and there is another side which is HE, and that is towards our left. So in this case, for the force on FG as well as force on HE, they are going to cancel each other. Okay. We can say no net force along vertical. Sorry, not along vertical sides rather. So vertical side basically means along horizontal, along x-axis. So therefore, we can say the net force the x component cancel each other, because we just said that along x-axis there will be no net force. So x-axis component cancel each other, and the y component, or we can also call that as y-axis, will be Fy is equal to Fgh plus Fef. We simply add them, we get f of y will be equal to I B naught Yc plus A by 2 minus I B naught Yc minus A by 2. And we get this as f of y will be equal to, we can take I B naught as common, so we are left Yc plus A by 2 minus Yc plus A by 2, and Yc and Yc cancels out, so we can write that our Fy will be equal to I B naught, and this comes as A. And value of current we already know, so we substitute here, we get this as B naught square A square V divided by R, and it is in upward direction. Upward means plus J. And now we come to the final part, that is the speed Vt and the terminal velocity. Part C. So we have speed Vt and terminal velocity. So there will be two forces acting on this loop. One will be a force of gravity, downward direction, and Lernau's force in the upward direction. So there will be net force which will be producing the acceleration. So we can write the forces. We have gravity, which is our mg minus of J, and we just calculated Lorentz force, which is our B naught square A square V divided by R, and this is upward direction, that is plus J. So net force will be equal to F. This gives me, as it is moving downward direction, so we are going to have mg minus B naught square A square V divided by R, and it is downward. And for F, we can write MA, and MA can be written as A can be written rather dV by dt. So we get M dV by dt is equal to our mg minus B naught square A square V divided by R. And we can just solve it. So this we can write it as dV upon, or yeah, we can just solve it. We can write dV upon mg minus B naught square A square V upon R is equal to dt upon m. And we assume a factor k, and this factor k is equal to B naught square A square upon R. So we get this as dV upon mg minus kV is equal to dt upon m. Now we simply integrate them from 0 to v, and we have 0 to t. So this comes as minus 1 upon k, and we have a natural log of mg minus kv (0 to v), and this comes as t upon m. We substitute the value, limits rather, and this comes as minus 1 upon k. We have natural log of mg minus kv minus natural log of mg is equal to t upon m. And we can write this further as we have natural log of mg minus kv divided by mg is equal to minus kt upon m. Now it is a simple calculation. We can write this as mg minus kv divided by mg is equal to e raised power minus kt upon m. Okay, so this comes as kv is equal to mg1 minus e, and this is minus kt upon m. So therefore the velocity vt is equal to mg upon k, and 1 minus e, and this is minus kt upon m. Now we simply substitute value of we can say equation for k, and we can write this as our vt is equal to, we have b naught square a square, and this comes as mgr 1 minus e, and this will be our minus b naught square a square upon mr multiplied by t. So this is the equation for velocity, and finally we can find out the terminal velocity. So terminal velocity is our, at t tends to infinity, the term e raised power minus entire term will tend to 0. Therefore the terminal velocity vt will be equal to mgr upon b naught square upon a square. So these were the two questions asked in the year 1999 and 2001. So this completes the questions. Thank you.